close your eyes and imagine the cool darkness of a forest floor at dawn, where the air itself feels thick with moisture and time. Around you, the towering trunks of ancient trees stand silent and waiting, their bark rough beneath your fingertips, weathered by countless seasons you cannot count. The ground beneath your feet is soft with decomposing needles and leaves, releasing that deep, earthy scent of renewal and decay intertwined. Your breath comes slower here, breathing in the thickness of the air itself, humid and cool even as light begins to filter above. The canopy high overhead breaks the coming dawn into shades of amber and green, and shadows drift across your skin like something almost alive. You sense the profound stillness around you, a patience so deep it seems to hum beneath your consciousness, and you understand without words that you stand among the oldest living beings on this planet. Everything around you grows, slowly, invisibly, in rhythms too subtle for human perception to capture, yet too powerful to deny once you have felt their presence in the silence. And now, as you settle deeper into this forest, let your awareness turn inward, just as the tree itself does. Within every tree lies a chronicle of time itself, written not in ink or stone, but in the grain and structure of living wood. Each year, as the seasons turn their ancient wheel, a tree deposits a new layer of growth, a thin ring that captures the story of that single year compressed into space measured in millimeters. This process, so fundamental to the life of every tree on Earth, operates in near-perfect silence, driven by forces as old as photosynthesis itself. The structure we call a growth ring is actually composed of two distinct parts, and to understand them is to understand the tree's seasonal struggle for survival. In spring, when warmth returns and daylight lengthens, a tree awakens from dormancy and produces early wood, also called springwood. The cells created during this eager season are large and thin-walled, optimized for rapid water transport as the newly expanded leaves demand vast quantities of moisture. These cells appear lighter in color, almost pale, as if painted with the optimism of renewal. Then, as summer progresses and eventually yields to autumn's shortening days, the tree's growth begins to slow and consolidate. Latewood, or summerwood as some call it, comprises the second part of the annual ring. Formed as the growing season winds toward its conclusion, latewood cells are smaller and possess thicker walls, creating a denser, darker appearance. This transition from the light earlywood to the dark latewood creates the visible boundary between one year's growth and the next, a subtle but unmistakable line that becomes visible in cross-sections of freshly cut wood. The boundary exists because the tree senses the shortening of days, a biological clock so precise that it responds to the mere diminishing of light hours, preparing itself for the dormancy to come. In this way, the very structure of wood carries within it the memory of seasonal change, encoded in cellular architecture. To truly comprehend the miracle of tree growth, we must venture into the invisible realm where molecules move and reshape themselves in patterns of extraordinary complexity. Imagine, for a moment, that you could shrink yourself small enough to float inside the tree's tissues, to witness the dance of water and nutrients happening in silence all around you. The primary systems responsible for a tree's expansion are the xylem and the phloem, and though their names may sound foreign and distant, they represent nothing less than the tree's arteries and veins, the very pathways through which life itself flows. The xylem is the tissue responsible for moving water and minerals upward from the roots toward the leaves, a journey that defies gravity through mechanisms that have fascinated scientists for generations. Water molecules possess a remarkable quality called cohesion, meaning they tend to cling to one another with surprising force. Imagine this as an invisible rope of water, stretching from the deepest roots all the way to the highest leaves. This cohesion, combined with the pull created by water evaporating from the leaves in a process called transpiration, creates a continuous column of water that seems to climb upward through sheer will. The xylem cells, which have died to become hollow tubes, serve as the perfect conduit for this water transport. Feel the coolness of this water moving upward, carrying minerals from the dark soil into the light of the canopy above. Each spring, as the growing season begins, new xylem cells are created by the cambium, the thin, living layer of tissue that lies just beneath the bark. This is where the true magic happens, in a layer so thin that you could barely see it with the naked eye. The phloem, by contrast, is the tissue that moves sugars and other organic compounds downward from the leaves to all the other parts of the tree. Where the xylem carries raw water and minerals, the phloem carries the synthesized nutrients created through photosynthesis. The fruits of the leaves labor in capturing sunlight. The phloem cells remain alive, maintaining delicate pressure gradients that push nutrient-rich sap through their specialized structures. Imagine touching the bark of a tree and knowing that beneath your fingertips, on the inside of that bark, lies a river of sweet, nutrient-filled sap moving downward, feeding the roots far below, feeding the cambium itself so that it may continue its work of growth. Between these two transport systems lies the cambium itself, a layer of meristematic cells so thin that it can barely be seen with the naked eye, yet so powerful in its activity that it shapes the entire future form of the tree. The cambium divides and redivides throughout the growing season, with each cell division creating new xylem toward the inside and new phloem toward the outside. This is growth made manifest at the cellular level, a process happening continuously during the warm months, each division a tiny step in the tree's annual expansion. A single cambium cell divides not once but dozens, hundreds, perhaps thousands of times during a single growing season, each division contributing another microscopic layer to the ring. The mathematical consequence of this cellular multiplication is the visible ring we see in cross-section, a testament to the sum of countless cellular events occurring in coordinated silence. And as you drift deeper now, imagine yourself small enough to witness this multiplication, to see the cambium at work, dividing and expanding in the darkness beneath the bark, creating wood with each beat of its invisible pulse. As the year turns through its ancient cycle, the tree responds to each seasonal shift with precise biological adjustments, creating within itself a record of climatic conditions that would have been impossible to preserve in any other medium. Spring brings warmth and moisture, the signal the tree has been waiting for during the cold months of dormancy. The ground thaws, water becomes available again to the roots, and the lengthening photoperiod, the number of hours of daylight, triggers the awakening of dormant buds that have been resting, waiting, patient. During these spring months, the tree dedicates enormous cellular resources to creating new leaves, and the earlywood cells reflect this prioritization. They are large, with relatively thin cell walls, optimized for the rapid movement of vast quantities of water from root to leaf. The tree at this time is in a hurry, racing against the calendar to maximize photosynthesis during the precious months when water is abundant and temperatures are favorable. Growth rings formed during this period tend to be wider than those formed later in the year, a visible testament to the tree's eagerness and the abundance of available resources. In wet springs, this early wood may appear particularly thick, while in dry springs, Even the early wood layer remains relatively narrow, a subtle indication of resource scarcity encoded in wood. Summer arrives with its long days and, in many regions, its dry heat. As the season progresses toward its peak, the amount of water available to the tree may begin to decline. You feel it as thirst. The tree feels it too, drawing water down deeper as the surface soil dries. Photosynthesis continues at high intensity during these lengthening days, but the tree must now be more careful about water conservation. The growth rate begins to slow from its spring peak, and the cells being produced become progressively smaller and thicker-walled. This transition is gradual rather than abrupt, reflecting the tree's continuous assessment of environmental conditions. The cells of midsummer latewood are denser than the spring earlywood, and this density makes them stronger, more capable of supporting the weight of mature foliage above and more capable of better resisting mechanical stress from wind. Autumn arrives with the inevitable shortening of days, and this change in photoperiod is the signal the tree has been waiting for, encoded in its genetics across millions of years of evolution. Day length is a more reliable indicator of season than temperature or moisture, and the tree responds to this signal by beginning to prepare for dormancy. Growth slows further, and the cells now being produced are small and densely packed, their thick walls creating a material that is nearly as hard as the early wood is soft. The color difference between the late latewood and the pale early wood of the following spring becomes the visible demarcation line between one year's growth and the next. In autumn, the tree also retrieves valuable nutrients from its leaves before they fall, a process that involves the breakdown of chlorophyll and the exposure of yellow and red pigments that had been hidden beneath. This retrieval of resources is not random, but carefully orchestrated, another example of the tree's sophisticated internal economy. Winter arrives and growth ceases almost entirely. The cambium, that thin layer of life beneath the bark, enters into dormancy. Water freezes in the soil and becomes unavailable to the roots, and the tree reduces its metabolism to the absolute minimum necessary for survival. The tree enters a profound sleep, and you too might imagine this sleep, this quiet rest, this gathering of energy for the spring that will come again. During the winter months, no new cells are produced, and the ring formed in the previous year becomes protected and isolated, awaiting the next spring's expansion to begin the cycle anew. Yet even in dormancy, the tree is not truly inactive. Internally, it is undergoing the complex biochemistry of preparing for the next growing season, accumulating reserves of stored sugars and proteins that will fuel the spring's awakening. These ancient trees hold secrets in their wood, and in the high mountains of the American West, where the air is thin and seems to burn in your lungs, there exists a tree so resilient and so ancient that it pushes the boundaries of what we understand about longevity itself. Imagine yourself at 11,000 feet above sea level, where the ground is bare rock, lichen-stained and ancient. Around you stand twisted, silvered trees, some alive but barely, their trunks spiraling with the contortions of millennia. You are in the presence of the oldest living things on Earth. These are bristlecone pines, found in the rocky slopes and ridges of the Great Basin, trees that have been growing on this planet for over 5,000 years, a span of time that encompasses the entire recorded history of human civilization and extends far beyond it. These trees stand as silent witnesses to epochs that predate the pyramids, the great cities of antiquity, and every empire that has risen and fallen in human memory. The extreme longevity of bristlecone pines results from a combination of factors that seem almost designed for endurance. They grow in environments so harsh and so resource-poor that few other trees can survive at all. The soils are thin and mineral poor. The growing season is brutally short, lasting perhaps only a few months, and water is scarce. Most importantly, their wood is extraordinarily dense and resistant to decay, rot, and insect damage. Even after a bristlecone pine dies, its wood can stand for thousands of additional years, creating the ghostly forests of dead, silvered trunks that appear in photographs from these high mountain regions. The growth rings of bristlecone pines are a study in subtlety and patience that will teach your mind to rest in the smallest increments. Where a tree growing in favorable conditions might add a growth ring measuring several millimeters thick, a bristlecone pine in its harsh mountain home often adds rings measuring only 0.1 to 1 millimeter in thickness. 1,000 years of growth might be compressed into a space smaller than the width of a human hair. In the most difficult years, when drought grips the mountains, or when a particularly harsh winter devastates the tree's resources, the ring formed that year might be so thin as to be nearly invisible to the naked eye, yet it remains a microscopic record of that year's struggle for survival. These trees are so slow-growing that their entire annual cycle of growth might be completed in the span of time it takes some other trees to grow a thick branch. Because bristlecone pines grow so slowly, their rings are extraordinarily sensitive recorders of environmental conditions. Each ring captures the year's precipitation and temperature patterns in the width and structure of its cells. A wide ring indicates a year of relative abundance, when moisture was adequate and conditions were favorable. A narrow ring indicates a year of stress and scarcity, when the tree could barely sustain itself. The sequence of rings in a bristlecone pine's wood becomes a continuous narrative of climate history, readable to anyone trained in the science of dendrochronology. A single bristlecone pine might contain 5,000 individual rings, 5,000 stories of individual years, stacked one atop the other, each telling its own small tale of survival and adaptation. Some of the oldest bristlecone pines in the world have been found to be over 5,400 years old, meaning they were already ancient when the ancient Egyptians were building their first monuments. Yet these ancient trees often appear twisted and gnarled, their trunks partially dead, while still maintaining enough living wood to continue growing at their characteristic glacial pace. Some have less than a ribbon of living bark connecting the living heartwood to the crown of the tree, a hairline thread of life sustaining an entire organism whose history spans the rise and fall of countless human civilizations. They are living calendars, each ring a year, each sequence of rings a story of climatic patterns that would have been impossible to preserve in any other format. These ancient trees hold secrets in their wood, and for thousands of years, humans could only wonder what those secrets might be. But then, one scientist asked a question that would change everything. It was not until the early 20th century that a scientist named Andrew Ellicott Douglas developed the science of dendrochronology, the study of tree rings to determine ages and past climatic conditions. Douglas was an astronomer who had become interested in how solar cycles might affect tree growth. And in pursuing this question, he inadvertently created one of the most powerful tools available to historians and climate scientists. The fundamental principle of dendrochronology is elegantly simple, and yet it opens doors to the deep past. Each tree produces one ring per year, with the width and structure of that ring reflecting the conditions of that specific year. By counting rings in a newly cut tree, one can determine the tree's exact age, reading its life as you might read the pages of a book, each page a year. But imagine now a scientist, eyes tired from hours of measurement, moving between cross-sections of wood, looking for the pattern. that distinctive sequence of rings that will confirm, yes, these two trees lived in the same era, their lives overlapping in time. The overlap is the key. Patterns in ring width can be matched between different trees, allowing scientists to create overlapping chronologies that extend backward in time far beyond any individual tree's lifespan. By extending this principle across multiple trees and sometimes incorporating wood from ancient structures like buildings or archaeological sites, dendrochronologists have created master chronologies that extend back thousands of years. The oldest continuous dendrochronological chronology for North America extends back over 9,000 years, created primarily through the study of bristlecone pines and other long-lived species. This chronology is so precise that it can assign a specific year, not merely a century or decade, to any ring within that timeline. An ancient wooden artifact can be dated to within a year or two of its actual age by matching its ring pattern to the master chronology, a precision that is difficult to overstate in its historical importance. The applications of dendrochronology extend far beyond simple age determination. Climate scientists use tree rings to reconstruct past climate patterns with remarkable precision. A sequence of narrow rings indicates a period of drought or other stress, while a sequence of wide rings indicates years of abundance. By examining thousands of trees from a given region, scientists can create a detailed picture of climate variations over centuries or millennia. Volcanic eruptions that injected ash and aerosols into the atmosphere create distinctive narrow-ring sequences that can be matched across continents, allowing scientists to date historical eruptions with precision. Archaeological dating using dendrochronology has resolved countless historical mysteries and confirmed or disputed the dating of important artifacts and structures. Imagine now standing before an ancient oak tree that has been standing in the same location for 300 years. Place both your hands on its bark. It is rough, almost warm in the afternoon sun. Your arms barely reach a quarter of the way around its girth. Close your eyes and lean your forehead against the wood. In the darkness behind your eyes, you are feeling 300 years of slow, patient growth. Each ring beneath your palms represents a single year of this tree's life. This massive trunk, wider than a person is tall, with its crown spreading across nearly a third of an acre, germinated as a tiny acorn in the year 1724, a time when the American colonies were still subject to British rule, when the Industrial Revolution had barely begun its transformative power, when the world population had barely reached 600 million. That tiny sapling pushed its first leaves into the spring air and began its patient work of photosynthesis and growth. Feel the weight of those centuries, the accumulation of wood, the slow triumph of survival. If we were to examine the heart of this tree in cross-section, we would find rings numbering approximately 300, one for each year of its existence. But these rings would not all be identical. They would form a narrative, a visual autobiography written in wood. The rings formed in the 1730s would likely be moderately wide, reflecting favorable conditions and the tree's youthful vigor. There might be a sequence of particularly narrow rings formed during a severe drought in the 1740s, a climatic event that left the tree stressed and struggling, but unable to relocate or escape. The rings of the 1750s might show recovery, widening as conditions improved, the tree gathering strength. Moving your awareness along this 300-year timeline, you might identify rings formed during periods of different climate patterns, when the tree's growth was influenced by environmental conditions quite different from those of recent decades. The rings formed in the 1800s might be notably thicker than those of later centuries. suggesting more favorable climate conditions, or perhaps less competition from neighboring trees that may have been removed or died. As we progress toward the present day, the rings become more recent and more precise in their dating. The rings of the 1930s and 1940s carry within them the signature of climatic conditions during the Dust Bowl years in America, a time when severe drought gripped vast portions of the continent. You might see narrower rings during this period, a physical record of the tree's struggle against aridity. Within this single ancient oak's wood lies an entire history, readable by anyone with the knowledge to interpret it. 300 separate rings, 300 individual years, each contributing its millimeter or fraction thereof to the total width of wood. The oldest rings, toward the very center of the tree, were formed when George Washington was leading the American Revolution. The most recent rings, those just beneath the bark, were formed last year and the year before that. This tree stands as a living archive, a silent witness to all the human events that have occurred during its lifetime, indifferent to human concerns, yet recording them nonetheless in the only way available to it, through the subtle modulation of its growth. As we explore deeper into the relationship between environmental conditions and the rings that record them, a more nuanced and sophisticated understanding emerges, one that allows us to hear the voice of the environment speaking through wood. The width of a ring is influenced by multiple environmental factors, and those trained in the art of reading these rings have learned to interpret them with remarkable precision. In arid regions, the primary limiting factor is water availability, so ring width correlates strongly with annual precipitation. A year with abundant rainfall will produce a noticeably wider ring than a year with drought conditions. Temperature, too, leaves its mark on tree rings, though the relationship is more complex and requires careful interpretation. In regions where the growing season is limited by cold, such as at high elevations or high latitudes, a warm year will produce wider rings as the extended growing season allows more growth. In regions where temperature is not the limiting factor, variations in temperature have less effect on ring width. The density of latewood, the darker portion of the ring, can also vary based on growing season conditions. A harsh, cold autumn that came early might produce denser latewood with thicker cell walls, while a prolonged warm autumn might produce more gradual transitions and softer wood. Volcanic eruptions and their effects on climate also leave signatures in tree rings, like footprints in sand. When a major volcano erupts and ejects sulfur aerosols into the stratosphere, these particles reduce the amount of solar radiation reaching the Earth's surface, causing a temporary cooling that settles over the land like a shadow. The year of the eruption and the following year often show noticeably narrower rings across entire continents, a pattern that allows dendrochronologists to precisely date historical eruptions. The eruption of Mount Tambora in Indonesia in 1815 left a distinctive signature in tree rings from around the world, a visible mark of climatic disruption caused by volcanic ash and aerosols, a scar that healed slowly over several years. Insect infestations, disease, and even wildfire can also leave marks on tree rings, and a patient reader learns to recognize these marks as the tree's autobiographical account of suffering and recovery. A severe insect outbreak that defoliated a tree and reduced its photosynthetic capacity would result in narrower rings during that infestation. The recovery from such an infestation is also visible, as ring widths gradually increase as the tree's vigor is restored. Partial death from lightning strike or wind damage can be visible in rings, as the tree redirects its growth to undamaged portions of its crown. These trees are incredibly sensitive recorders of environmental conditions, and the more deeply we learn to read them, the more history and climatic information we can extract from their silent testimony. The manner in which a tree expands its rings follows geometric principles that have fascinated botanists and mathematicians alike, patterns as orderly as the spiraling of a nautilus shell. The cambium, that thin living layer, produces new wood in a radial pattern, meaning that new rings are formed concentrically, with each new ring surrounding all the rings that came before it. This creates a fascinating mathematical property that reflects the tree's expansion through space. Consider a tree with a cambium at radius r from its center. In the first year, the tree produces a ring of width w, so the cambium moves outward to radius r plus w in the second year. The cambium, now at this new radius, produces another ring of similar width w, which increases the circumference further still. The circumference of a ring at radius r is 2 pi, so the total amount of new wood produced in a given year increases with the tree's age and size. This means that as a tree grows, each year's ring contains more total wood than the previous year's ring, even if the rings appear to have the same width when viewed in cross-section. A century-old tree produces rings with more total volume of wood than a young tree of the same species, even if the rings themselves look similar in width. The tree's growth accelerates in the geometry of space, even as the cambium maintains a steady pace. This geometric reality has important implications for understanding tree growth and energy allocation. As a tree grows larger, supporting that increased mass and size requires more resources than ever before. Yet the tree's ability to capture energy through photosynthesis depends on its leaf area and the intensity of photosynthesis in those leaves, which does not scale perfectly with trunk radius. Large trees must allocate a greater proportion of their annual growth to wood density rather than ring width, focusing on creating stronger, more durable wood that can support increased mechanical stress. The spiral pattern of growth in some tree species adds another layer of complexity to this geometric dance. Some trees exhibit spiral grain patterns, where the cellulose fibrils that comprise the cell walls are oriented in a spiral rather than vertical pattern. These spiral grains can be the result of the tree's response to mechanical stress, such as wind, or can be a genetically determined characteristic of the species. The presence of spiral grain affects the wood's strength and flexibility, and the degree of spiraling can vary between rings, creating visible variation in the wood's appearance. These patterns are also environmental records, subtle indicators of the mechanical stresses the tree experienced during the years when those cells were being produced. The pioneering work of Andrew Ellicott Douglas created the foundation for what modern dendrochronologists call the International Tree Ring Database, a vast compilation of ring data from thousands of trees across dozens of countries and multiple continents. This database now extends backward over 12,000 years in some regions, creating a continuous record of past climate conditions that predates written history by thousands of years. The precision of this record has transformed our understanding of natural climate variability and has provided essential context for interpreting modern climate change, allowing us to see our present moment within the vast arc of deep time. Different tree species have been used to extend the dendrochronological chronology backward through time like links in an ancient chain. In North America, the bristlecone pines provided the crucial link extending back over 5,000 years. In Europe, oak trees from ancient structures and archaeological sites allowed researchers to extend the chronology back thousands of additional years. In the Mediterranean region, ancient olive trees and other long-lived species contributed to the record. In tropical regions, different methodologies have been developed, as tropical trees often do not produce clear annual rings due to the more uniform year-round climate, yet patient scientists have found ways to read their histories too. This global chronology has revolutionized paleoclimatology, the study of past climates, creating a voice for the past that speaks through wood. By analyzing the patterns of wide and narrow rings across centuries and millennia, scientists can identify periods of widespread drought, periods of unusual warmth or cold, and the temporal extent of climatic variations that might have seemed random when viewed from a single location or single tree. The medieval warm period, roughly from 900 to 1300 CE, shows up as a pattern of relatively wide rings in tree ring records from across the northern hemisphere, indicating that this period of relatively warm conditions was indeed real and continental in scale. The subsequent period, called the Little Ice Age, roughly from 1300 to 1850, shows up as a corresponding pattern of narrower rings, indicating cooler and often wetter conditions across much of the world. This period, when temperatures were perhaps only a degree or two cooler than the medieval period, had profound effects on human history, influencing agricultural patterns, migration patterns, and the rise and fall of civilizations. The tree rings allowed scientists to document this climatic variation with precision and to understand its duration and geographic extent in ways that were impossible before dendrochronology was developed. And so we arrive at the present moment, where countless trees across the planet are right now engaged in the same process that has been underway for hundreds of millions of years since trees first evolved. The cambium of every living tree is producing new cells, expanding the rings with each passing day and week. The oak tree standing in a park in your nearest city is growing its ring for this year. The bristlecone pines of the High Sierra are slowly adding their gossamer-thin rings to their already ancient trunks. The vast forests of the Amazon are creating their rings in patterns that will later be analyzed by scientists seeking to understand changing climate patterns. Each ring being formed right now will become historical data to future scientists who may study the wood of today's trees centuries from now. The environmental conditions of this decade, this year, this very season are being recorded in wood, encoded in the width and density of cells being laid down by the cambium. A future dendrochronologist, perhaps centuries from now, will look at the rings being formed today and will be able to determine with precision the exact year in which they were produced, and will be able to infer from their width and structure information about the climate conditions of our time. The largest trees on Earth contain the oldest wood, and within that wood lies layer upon layer of history compressed into space. Some of the giant redwoods of California have been growing for over 3,000 years, their massive trunks containing 3,000 rings, each one a chapter in a story that began before Rome was founded as a kingdom, before the pyramids were conceived, before agriculture had spread across most of the human-inhabited world. These trees stand as living monuments to patience, to the power of consistency and persistence across vast spans of time, to the quiet accumulation of growth through millions of daily photosynthetic moments. The process of tree growth, so invisible and so patient, continues regardless of human awareness or attention. Trees have been growing and forming rings for millions of years before humans evolved, and they will continue doing so long after human civilization has passed from the earth. Yet in our brief moment of coexistence with these organisms, we have been granted the extraordinary gift of being able to read their history, to understand the stories written in their wood, to glimpse through them the deeper patterns of climate and environment that have shaped and continue to shape the living world. The rings continue to form, one layer each year, in near-perfect silence. In the darkness beneath the bark, in the invisible domain of the cambium and phloem, the story of each year is being written in wood. These silent growth rings accumulate not with fanfare or announcement, but with the steady, patient persistence that characterizes all of nature's most profound achievements. They are growing now, this very moment, in forests you may never see, in trees you will never touch, recording in their structure the unfolding narrative of our world. And as you drift now into deeper rest, allowing your awareness to settle and soften, imagine the stillness of the forest, the quiet patience of ancient wood, the slow and invisible miracle of growth continuing its eternal work beneath the bark of every tree. The rings expand, year by year, season by season, each one a record of time passing, a memory held in the language that only trees can speak. Your breathing deepens and slows, matching the tempo of growth that happened so gradually that no human eye could see it changing, yet changing nonetheless, relentlessly, patiently, throughout the centuries. Feel yourself sinking deeper into the stillness, the profound quiet where all growth happens, where time becomes wood, where silence becomes story. The rings expand in the darkness beneath the bark. Growth continues. Time passes. The forest breathes. Final word count, 6,110 words.